Welcome students, and in this video we are going to talk about elementary functions and which is a complex log. Okay, now this is one of the most important functions which you can learn, and it is very different from what we know in real line. Okay, let's just understand. See, the question which you want to answer is this. The question is this. So given z, okay, z which looks like x plus iy, clear? In C as a complex number, given a complex number, we want to define what is log of z. You understand? So we can also write it as log of z. Yeah, we want to define something like this. Now you do realize that if you want to talk about the negative number, let's say negative real number, and you want to talk about the log of that thing, then we have issue. Again, log 0 also there is a issue, right? We can't define all this. So essentially, we want to generalize the idea of log from real to complex in such a way that it preserves, whatever we know from the real line. Okay. Now, what we know from real line is what is this? What is log? So essentially, we define it like this. See, we want to define it. So this is the question. Define log of z. Okay. And how do we define it? If you remember, essentially it is defined as the inverse of exponential function, right? And exponential in our case is already been defined. We did this in the earlier video. So essentially, given that particular exponential, the complex exponential, we are going to define the inverse function of that, which we are going to call it as a logarithm. So what is it? That is you see, let's say that I want to define this thing, right? Log z, clear? And let's say that is a w. So I want, see, log z is another number which is we are trying to find it as a complex number w, right? Yeah. So this is the question. So essentially, given a z in C, we want to calculate what log of z is. Yeah. And how do we do that? So let's get the idea of it. So you see, essentially what we are going to do is log of z, yeah, we are going to define it as w. Now, of course, z has to be non-zero, yeah, non-zero, because log of 0, you do realize log of 0 is not defined even in real, yes. So here we are going to define log z as w and z is not equals to 0, yeah, because you see that 0 in C you can actually identify with r also, right? So this is there. So log z is w. Okay, now if that is the case for z not equals to 0, then that will imply that, you see, we will define it. Yeah, it's defined. So let me put it this way. So log z equals to w is defined by the relation. But how is it defined? It is defined by exponential of w equals to z, exactly like what we do in R. So essentially, if it's a given z, we want to find log z. So essentially, we are looking for a w such that exponential of w is that z. Yeah. Now, why z not equals to 0 is this? See, if z equals to 0, then see, e power w, yeah, that is not, see, since e power w is not 0, okay, for all w, okay, in that case what happens? Z equals to 0 is not going to be possible, clear? Okay, now see, this w, yeah, is what we want to find. Yeah, given a z, we want to find the w such that this happens. So w is where, by our definition, we are assuming w to be in C. Yeah, that will imply that w should look like u plus iv, u plus I times v. I hope this is clear. Yeah, and let's just call our z to be r e power I theta. Yeah, this is what our definition is. Then what happens is, then what do we get? We get e power w, yeah, is e power u plus I v, right? And this is nothing but r e power I theta. I hope this is clear. W is what we need to find. Once we know what w is, then we know what log z is, right? Now, if that is the case, we can write w as u plus iv and z as r e to the power I theta. Yeah, and then e power w is e power e plus iv, which is r e power I theta. Okay, fine. Now you see, if you take the absolute value, so taking absolute value, what do you get? Absolute value. In this case, if you take absolute value, this turns out to be r. If you take absolute value here, what is this? This is e power iv. E power iv, the absolute value is going to be 1. So essentially, r is nothing but e power u. So therefore, it will give you e power u equals to r. Okay. And what is v? In this case, v is going to be theta. I hope this is clear. This is not very difficult, right? Okay. So that is there. Okay. So you see, since e power u is r, now you see what is u? Since u is in r, u and v is in r, right? U is in r, so e power u equals to r. See, small r is also in r. Okay, so this relation is our real relation. So we know how to handle this. So this will imply that u is nothing but log of r. Yeah, this is very, very well defined. It's a real logarithm. Yeah, very well defined. No issues there. Okay. So therefore, see, what do you want to find? We want to find w, right? Yeah. So what is w? W is nothing but log of z, which is u plus iv. Okay. What is u? U is log of r. See, r is what? The absolute value of z, right? So log of r plus plus I, and what is v? V is nothing but theta. Here, theta. Okay. So here you see what is r? R is nothing but the absolute value of z, which is always going to be 0 because z is not 0. This is what we are assumed, right? And what is theta? Theta is nothing but the argument of z. Yeah, of course it is. Yes, you see, theta is v. V is nothing but the argument of z. Okay. So that is there. Now you see, you do realize that this theta, yeah, this since this is just the argument of z, okay, so we can actually replace it by integer multiple of 2 pi. Okay, so therefore, hence the complex natural logarithm okay, log of z, okay, again z is not 0, please remember z is not 0, yeah, is infinitely valued. Okay, so what do I mean by this? Since this argument is theta plus minus 2 pi I, so we can just write it like this. So you see, if you take the principal value, let's just take the principal value. So we'll define it like this. Donate ln, this is capital L, capital L n of z. So the logarithm. So this is called the principal value okay, of the complex log. Yeah. So and how, what is it? It is basically your z. So given by log of z is nothing but log mod z. This is r is mod z, plus I theta is already there. So I times the capital argument of z. Here, the principal argument, that is. Yeah. So that is how we are defining the log of z. See, this theta is basically the argument. Yeah. So when that theta becomes the principal argument, then we call it a principal logarithm. Yes. And any other logarithm, and you see, you can define a log, just a general log, log z, as the principal logarithm log z plus minus 2n pi I. I hope this is clear. N equals to 1, 2, 3, and it goes on. Yes, see, these actually takes care of the theta part, and then there is plus 2n pi, right? So that is why plus minus 2n pi I. So essentially, any log is capital log plus minus 2n pi I. Okay, the integer multiple, that is. Yes. Okay, so one thing to note that they have the same real part. The real part you see here log z, here the log z. Okay, so the thing is the real part is here, the imaginary part actually that differs by an integer multiple of 2 pi. That's what's happening. Okay, now some properties. Let's just look at some properties. See, what we did is we actually generalized the idea of logarithm from R to C. Now the question is this generalization valid? Is it okay? So let's say if Z is in R plus, okay? So basically what I'm trying to say is this, it is a positive real, yeah? Then what is the principal argument of Z? We have already talked about it. If it is in positive, so essentially let's say anywhere here, yeah, Z. Okay, so what is the argument? Principal argument in this case is 0, right? And then you see the complex log, okay, complex log, the principal log, or the complex log anyway. So the principal log or the complex log, let's just write it log of Z, the principal log. So what is it? In this case, it is nothing but log of mod Z. Okay, so essentially the principal log is exactly the logarithm which we know. You understand? Now what happens is this, since this is complex, you actually end up getting more such values of in terms of 2 and pi. Okay, right. Number 2, if Z is negative real, yeah, so positive real is there, what about negative real here? Okay, if Z is in R minus, huh? So of course Z is not 0, huh? That is where log is not defined, so that we're not talking about that. Okay, see, the natural log is not defined. We don't know what is the negative logarithm of negative real number, right? Huh? Now what happens is this, you see, then the principal argument of that, what happens to the principal argument of Z here? It is pi, right? If a number is over here, the principal argument is going to be pi, right? Okay, so argument of Z is pi, and what is the, I mean, you know, the principal logarithm? It is nothing but the log of mod Z, the real part, plus pi I. Yeah. So this is what we are getting. See, the thing is we have generalized the idea of logarithm. So previously we didn't knew how to define the log of a negative number, but now we know. What is it? It is the log of mod Z, the basically the absolute value of the Z, plus pi I. This is what you add. Okay, right. And one thing, you see, 3. From this particular thing, capital log of Z is nothing but, where is it? One second. Huh? Let me get it. Yes, here. See, the logarithm of Z is nothing but log of R plus I theta. Clear? This we already know. So, if you want to write out what is log e power log Z, then you can see that you can just write it down. You are going to get that to be Z. Okay, and this is what we expect, right? E power log Z has to be Z. So this is always true. Yeah, absolutely no issues. Okay, now is this the only way? You see, what is happening here is this argument of Z. Please understand this thing. See, the argument of e power Z since equals to y plus minus 2 n pi. Okay, so it is a multi-valued function, right? So if you take e power Z and look at the argument of this thing, that is basically y plus minus 2 n pi. Yeah, so this is multi-valued. So this is multi-valued. Hence, if you take log of e power Z, let me put it here, log of e power Z, okay, that is nothing but Z, okay, plus minus 2n pi I. Okay, so n equals to 0, 1, 2, goes on. I hope this is clear. Okay, maybe I can put it as a b. Okay, so e power log z is nothing but z, and then if you want to take the log of e power z, that is nothing but z plus minus 2n pi I, because you see the thing is this e power z, yeah, that is a complex number that we already defined. Now I want to find the log of that complex number. That is always going to be just a simple log, just general log. So that is going to be, of course, z, that part is there, yeah, but it is also going to take out the plus 2n pi term, plus minus 2n pi term, right? Okay, the 2n pi multiple. Okay. Okay, so that is about whatever we want to do in terms of log. Now what we will do is we look at some more properties. Okay, 4. Okay, what about log of z1 z2, z1 z2? Yeah, you can easily see it's not an issue, that it is going to be log of z1 plus log of z2. Okay, of course it is assuming that z1 and z2 no one can be equals to 0, because then log is not defined. Yes, and the fourth part is log of z1 by z2. What is it exactly? What you have guessed, it is log of z1 minus log of z2. Yeah, again here it is given that z1 z2 is not equals to 0. Okay, so those properties are always there, very nice properties, they're there. Okay, now once very important topic we want to talk about. Okay, so as a function, so now define this function, define f of z, okay, to be log z, log z. Of course, z is not equals to 0. Okay, now the question is this question. So is f continuous, okay, in c minus 0? Okay, c minus 0, what do I mean? C, at the point 0, log is not defined. So there is no point talking about the continuity of f at 0, right? So that we can just throw away 0. But except that everywhere it looks like it is defined. Yeah, that is what we have found, it is defined. So the question now is the function log which we have just defined, is it going to be continuous or not? Okay, in that whole thing. Okay, so from R we know that log is a continuous function. Okay, but here we want to see. So what is the domain here? Let's just understand this thing. The domain is this. Everywhere in C except this point. Okay, this point is not there. Okay, now see, take any, so you can see that if you take any point here, so let's say that first of all, let's just start with this thing. Okay, define a domain D. Okay, D to be C minus, I will take this, all of this except this line. Okay, so let me put it in red, except this line. So negative real and 0. Here, negative real and 0. Okay, so I will define it like this. So C minus, so Z is not equals to 0 or negative real. Negative real. Is this okay? Yeah. So we are taking all these. So this is our D. This is our D. Let's just call it D like this. Okay, the new domain, which is all the points in C minus the exact this particular axis along with 0. Yeah. Now in this domain, you take any point in this domain. So let's say I'm taking a point here from, let's say, z0. Okay, can I define log of z0? Of course I can. What is it? Log of z0 in this case is nothing but the real log of the absolute value. Yeah, plus I times, so I am just defining it for the general log. So I times the argument of z0. Okay, the I times the argument of z0. That's what we have, right? So, or we can just write it like this. See, this is nothing but half times log of, okay. So let's say that assuming z0 is x plus iy, sorry, x naught plus I y naught. Let's just assume that. Let's see. So let me write it properly. So it is half times x square plus y square, x square plus y square, okay, plus I times tan inverse y by x plus c, y by x plus c. Yeah. Now, from the very definition itself, you see that if I am taking z which is not 0 or z is not a negative real number, then all of this term, the real term, so let's just call it u of xy, okay, plus I v of xy. Okay. Now, you don't have to worry about it that u and v are both continuous functions in the given domain D, right? There is absolutely no issue. See, this is continuous, that part is continuous, okay? This part is continuous. Where is it? This log of x square plus y square, because all in this whole domain D, this is also defined, this is also defined, they are all both okay. Here C is the 2 pi multiple, is the multiple of 2 pi. Okay, so you see, this is continuous, this is continuous, so both of them are continuous, and hence what happens is we have, therefore, log of z naught is, so log is continuous at the point z naught, log of z is continuous at z naught, at z naught, which is in D. So basically, and z naught is arbitrary, so basically log z is continuous. That will imply log z is continuous in D. Okay, this is always there. Okay, now you see, so essentially it is always continuous function anywhere. Now what happens at a point here? So let's say if I take a negative real, negative real. So basically I am taking a x, okay, which is less than equals to 0 and y equals to 0. Let's just say take something like this, okay. So now let me put it in red, red. Now assume that z naught is equals to x naught, okay, which is less than equals 0. So basically here I am assuming y naught to be 0, okay, and x naught is negative. So basically somewhere here, okay. In that case, what happens? Let's just look at it. Fine. So again, take, okay, so now what we will do is we will take two sequence. One sequence will go like this towards this point. So this is x naught, this is x naught, and one sequence will go like this towards this point. Clear? Okay, so the first sequence is, it looks like this. So take Zn, okay, two sequences. So this will be Zn, Zn. And what is Zn? This is x naught plus I times, so take any point here, let's say any point here. This is x naught, and here it is, this point is y naught, this point, this is y naught. Let's just assume that. Or you can take any point here also. It is x naught plus, let's say, y1. Yeah. So this is one point. Now I want to, and yn, let's say, yn, sorry. So this is xn, and this is x naught plus, this is x naught plus iyn, and this is x naught plus iwn. Let's just assume this thing. Okay, so let zn be x naught plus iyn. Okay, this is in the third quadrant. Okay, so let's just call this is as d1, d2, d3 and d4. Okay, the quadrant I am just defining. So let's say this is in d2, okay, such that yn goes to 0. Yeah. So you do realize as yn tends to 0, that will imply that zn goes to x naught. Clear? Okay. So along this path, if you are going along this path, what is the logarithm? So let's just calculate the logarithm log of Zn in this case. Okay, this is nothing but log of x naught plus I yn. Yeah, and that is nothing but, you see, if you calculate this whole thing, it is nothing but log half, sorry, this is half of log of x naught square plus yn square, okay, plus I tan inverse of, so tan inverse of yn by x naught, okay, plus c. Yeah, for now I will just assume that c to be 0. So basically I'm just taking the principal log, huh? Or if you want, you can take another thing, it's not a problem, but let's just assume this thing. Yeah, so okay, so let's just take one log, huh? Just one part. So you see, if you start here, so it will be n equals to 0. So I'm just taking it to be n equals to 0. So this is I'm taking the principal branch, principal value. Okay, so I tan inverse yn by x naught. Now you see, if yn goes to 0, this whole thing, this actually converges to half of log x naught square, which is nothing but log of x naught. Okay, sorry, mod x naught. Okay, so this is there. Okay, so in this case, what is happening is this: from here, if you are approaching, you are actually approaching log of x naught. Okay, I have missed plus I times pi, plus I times pi from here. Okay, plus I times pi, because it is negative, right? So plus I times pi. Okay, now what happens again, Wn, if you define it to be x naught plus I yn, and I will define it to be Wn. Huh? So okay, again take another sequence Zn, take Zn to be x naught plus I Wn. Huh? This is in D3, huh? Such that Wn goes to 0. That will imply that Zn again goes to x naught. Yeah. So what am I doing here? Now I am going in this direction, Okay. But in this direction, you see, the argument of all these Zn's, yeah, they are going to be minus pi, right? If you remember, they are going to be, so we are taking it from that particular direction. So you see, log of Zn is nothing but log of x naught plus I Wn. Okay, this is nothing but half of x naught square plus Wn square plus I times, okay, tan inverse of Wn by x naught. Okay, so again I am taking just the principal value. Okay, so you see, x naught is in negative axis. Huh? And this Wn, this is also negative in this case, right? Okay. So what happens is this particular thing, you can see that this becomes, sorry, there is a log I have missed. There is a logarithm, half log. Okay, so this becomes log of mod x naught. Of course, that is true, it's not a problem. But here, this is not pi anymore, but this actually converges to, sorry, I should write it like this. This converges to, this also I should write it as this converge. Yeah, this is fine. This converges to minus I times pi. Yeah, principal branch. So you see, just think about it this way. See, argument from here, if you are going for every number here in this particular quadrant D2, the argument is actually going towards, so if you are converging to this point, the argument is always positive, to going towards pi. You understand? The argument part, the imaginary part. But if you are going through this way, you are approaching this point, what is happening is this: the argument is going to be minus pi, right? for any point here, if you are approaching by this, the argument actually converges to minus pi. So you see the same thing here by two different sequences. One sequence it will go to log of mod x naught plus I pi, and the other sequence will go to log of mod x naught minus I pi. So in that case, what happens is this. So we have actually obtained two different sequences such that they actually go to different. So basically, see continuity, what does it say? It says, so continuity means that for any sequence Zn converges to Z naught, f of Zn must converge to f of Z naught for any. So this is always true, right? Then f is continuous. If we can show this is continuous. But we have shown that there are two different sequences which actually converge to the same Z naught, but f of Zn does not converge to f of Z naught. Here it goes to plus I pi, here it goes to minus I pi. So in this case, what is happening is this function is not going to be continuous. Hence log Z is not continuous. I did it for just the principal log, but you can, I did not write it, but I just did it for the principal log. But you can just take any other log. So basically, you can take plus 2 pi or minus 2 pi, doesn't matter. You take from any other point, this is going to be the exact same thing. So log Z is not continuous for Z, of course, not equals to 0 or negative real. Okay, fine. So I hope this is clear. Now what we are going to do is we are going to look at another very, very important topic. What about differentiability? Differentiability. Of course, you can see that since this is not continuous, there is no way this is going to be differentiable. So that is always true. Yeah. But what I'm going to do is I'm going to show you another way of looking at it. Yeah. Okay. Let's just assume that we don't know anything about continuity, but we are just looking at differentiability. Okay. So in that case, what happens? See, the thing is, what did we show? We showed that log is continuous everywhere in C minus that particular line, right? So what about differentiability there? Can we say this? So let's see. You see, if Z is not zero or negative real, then log of Z is nothing but log of R plus I theta plus C, right? What is C? C is the 2 pi multiple, okay, which is nothing but half of log x square plus y square plus I times tan inverse of y by x plus C. Okay, yeah, C is 2 pi multiple. Okay, now if you just look at it like this, you see what is u of xy? Here u of xy is nothing but log of x square plus y square times half. Okay, and v of xy is nothing but tan inverse y by x, okay, plus c. Okay, therefore what is ux? It is nothing but, you can check that it is nothing but x by x square plus y square, right? It's very simple. And this is nothing but v of y. Please check. Also, what is u of y? U of y is nothing but y by x square plus y square, which is nothing but minus v of x. Again, check this part. Yeah, it's very simple, very easy to check. What does this say? This says that therefore the CR equation holds, right? Holds. Okay, holds. But is this okay? I mean, can you say that if the CR equation holds, this is fine? Yes, it is. Why? Because we have already talked about it. If you remember, you see that, let's say, what is the criteria for a function to be differentiable? Yeah, in terms of CR equation, we have already shown that a function. So essentially, what do we have is, let me write it this way. So you remember that if f can be written as u plus iv, u and v are real valued functions. Okay, uh, with continuous first derivatives, first partial derivatives, partial derivatives, and CR equation holds. Then we know that will imply the f is differentiable. Yeah, if you remember, we did it in some earlier video. Please go back and try to look at it if you forget about it. So essentially here CR equation is satisfied. What about u and v with first partial derivatives? You look at this thing. Yeah, this is a infinitely differentiable function in terms of both x and y. So the first order partial derivative exists and they are actually continuous. What about this? Exactly, again the same thing. They are all going to be continuous. Okay, no issues here. Okay, right. So in this case, what is happening is this: this theorem is satisfied, and hence f is differentiable. F is what? What is f? F is your log. Differentiable for z not equals to 0 or negative real. Okay. Okay. So that is there. I hope this is clear. Yeah. Okay. So what is the derivative? If you remember, what is f prime? If you want to define the, f prime, which is nothing but ux plus ivx, right? So in this case, therefore, if you also find out, if you want to find out what is the derivative of log, so basically the log of z prime is nothing but ux plus ivx. Yeah, just take the derivative and put it there. It is basically x by x square plus y square plus I times, so let me put it this way, minus y by x square plus y square. Okay, if you write all of this together, this is nothing but 1 by z. This is exactly the similar thing which we want actually. Yeah, right. And you see, for every one multiple, so since log of z, what is log of z? Log of z is nothing but log of mod z plus I times theta plus 2n pi, right? That is what we have. So if you fix a theta n, so let's say n equals to 0, then you get that the principal log of z is nothing but the principal log of z. N equals to 1, you get another log of z, which is nothing but log of mod z plus I times theta plus 2 pi. Okay, and you can go on doing this thing. You understand? You can go on doing this thing. So you see, each one of these functions, okay, so if you take n equals to 0, n equals to 1, all these things, if you take that, they are called the branch. So each of these functions is called the branch of Laplacian, is called the branch of the logarithm, Yeah, you understand? These are branch. So essentially one branch will give you the principal, the second branch will give you I theta plus 2 pi, and it will go on doing this thing, right? The third branch will give you theta plus 4 pi, another branch will give you theta minus 2 pi, it will go on doing this thing. Okay, and this of course is called the principal branch. of log z. Yeah, I hope this is clear. So of course, for n equals to 0, whatever the principal log is, that is your principal branch, and everything else, that is called the the other branches of logarithm. Okay. Now you see, you do realize that that particular line, you see, this particular axis, this axis, this is a problematic axis, right? This is a problematic axis. This is the problematic region. Which region? Only z not equals to 0, sorry, z equals to 0, z equals to 0 or negative real. Negative real. Okay. Okay. So in this case, what is happening is this, if you cut this part up, okay, if you just throw this part up, everywhere else log is differentiable, right? So this part is called as the branch cut for log z. Okay. So this is called so essentially we will call this as a branch cut of log z. Okay, branch cut. Because you do realize, you see, if you go via this, this actually works like a stairs. If you go via this, okay, so you end up along this line, you will end up going a little higher, right? Okay, so and this is where the exact problem is, because we have identified that it is not continuous at that line, neither does is it differentiable, right? So essentially this particular line we will going to say that this is a branch cut. Yeah, because you see, within this line, so basically you get 2 pi difference between logarithm within this line if you go via different paths. Okay, so now we will also talk about what general powers of complex numbers are. So the general powers of complex number, general powers of z in C. Okay, so what we want to do is this, given z is x plus iy, okay, we want to define, so we define z to the power c. Yeah, z to the power c. Of course, what is c? C is also a complex number. Z, of course, not equals to 0. So c is in capital C and z is not 0. Okay, so for a non-zero complex number, we want to define what z power c is, and that is of course defined as we do it in real, which is exponential of c log z. Clear? Exactly the similar sort of thing. Now you see, this log z, this has infinite values, right? So therefore z power c also has infinite values. Okay, so we will say that the principal value of z power c is nothing but e power c capital log of z, the principal log of z. Yeah, so this is the principal value of z power c. Okay, now what are the properties? See, if c is nothing but a natural number n, which is in n, you can have it, right? You can think of it like this. You do realize that in that case, then z power n, that is going to be single valued, exactly what we intended. In real line also exactly similar sort of thing happens. So this is single valued. Okay, why? Because in that case it becomes log of z. Yeah, so z power c is nothing but e power n log of z. Okay, so it's a single valued thing, so it's not an issue. Okay, so if number b, say c is a negative real, so c equals to minus n, n is in n, let's just assume that. Then also z power n is single valued. Okay, and these we already know, right? We talked about z power n, z power minus n, so that's literally no issues. Okay, What about C, which is 1 by n? C, let's say, is a fraction which is 1 by n. And n equals to 2, 3, all of this. C is not equals to, so basically, n equals to 2, n equals to 3, that sort of thing. Yeah. Then z power c, what is z power c in this case? It is nothing but nth power of z, right? Nth power of z, which is nothing but exponential. So this e power c log z. So basically 1 by n log z. Yes. See, since it is log z here, yeah, this is actually 2n, that 2n multiple is there, right? So you get the, so here you get n distinct values of the nth root. I hope this is clear. Okay. So you see, generally what is happening is this: z power c is always going to be infinitely valued. Okay. Right. Now, let's look at one other example. Example. Okay, what is I power I? Let's just calculate this. It's very, very important thing. What is I power I? Okay, I is complex, I is also complex. So basically, I power I want to find out. So this is nothing but, you see, e power I log of I. You see, this is the definition. C is I, log of Z is I. So e power I log of I. Okay. And we are not talking about the principal value, just any general exponent log, right? So e power I log of I. Okay. This is nothing but e power I. What is log of I? Log of I is nothing but log of I is log of mod I. Mod I is 0. Sorry, mod I is 1. So log of 1 is going to be 0 plus I. Then you have I. So here it is, the argument is going to be pi by 2. So it is I pi by 2 plus 2n pi, the, the 2 pi multiples. So essentially this is pi by 2. Pi by 2. See, log I, this is gone. So I times this. So this is I times pi by 2 plus minus I times 2n pi. This is there. So this will actually give you e power I times I minus I. So basically minus pi by 2 and then minus 2n pi. Okay. This is what I am getting, plus minus 2n pi. Okay. So these are all the values of I power I. So basically I power I is not a single value, but it has infinitely many values. Yeah. These are, but the thing is this, see, these are all real. This is a brilliant thing. These are all real valued. So I is complex, but I power I, if you do it, that's going to be real. And the principal value, what is the principal value? We talked about it. Principal value is nothing but n equals to 0. So if you put n equals to 0, the principal value of I power I is going to be e power minus pi by 2. So again, that is going to be real. So you see, even a complex number I, if you push it towards the power of a complex number also, so it is purely complex, it will actually end up giving you, e power minus pi by 2, which is real. So, things are not, I mean, they are generally, very bizarre here. Okay. Right. One question I want to ask you, that question, is log entire function? Very easy question. So if you remember, why the whole idea of asking you this question is this, that you should know what entire function is. Entire functions are functions which are differentiable at every point in C. Okay. So is log an entire function? Okay. If not, what are the entire functions which you, so basically, identify some entire functions. So this is the first problem. The second problem is identify some entire functions. functions. Okay, so first of all you have to answer whether log is entire function, and then you have to answer whether is you see the z power c, is this entire z power c. So basically this c, if fz equals to z power c is entire. So do all that, find out if log is entire, if z power c is entire, and also find out whether you can find some entire functions or not. If these two turn out to be not entire, if that happens, then can you find any other entire function? Okay, so with this I am going to end this video. Thank you.